Hi there, guys. I'm going to look at question 2 here for exercise 14b. This is hypothesis testing with the binomial distribution. Okay, so a big issue with this question when I'm looking at it is the alternative hypothesis. I think that that's not clear, but we'll see that as I go through the example. And I'll kind of match up to the answers in the back of the book for this one. So let's just have a look at what it says. It says a medicine company claims that its treatment leads to a significant reduction in symptoms within 1 week for 60% of patients taking the treatment. Okay, and then in order to test this claim, a trial containing a sample of 30 people will take place. So this is the null hypothesis. This is what we think happens in the population, that 60% of all people who take the treatment experience significant reductions, and we're going to test this claim with a sample. Okay, so the sample is for 30 people, and either each of those people will experience symptoms or they won't. And they'll experience symptoms with a probability of 0.6% according to the claim. So the null hypothesis will say that the probability of experiencing symptoms is 0.6. Now, this obviously is a binomial distribution because we have a number of trials, we have 30 of them in fact, and we have a probability of success for each of those trials. The success represents the significant reduction. Okay, so we definitely know that we've got this. And I also work out this at the top. The expectation here is NP, of course, and that's just saying that we would expect with 30 people to get 18 people with a reduction in symptoms according to the claim. Okay, now this is the difficult bit, and it says if P represents the proportion of people who benefit from the treatment, so 60% presumably according to the null hypothesis, then state the null and alternative hypotheses. Now, when I first read this, I thought that this would simply be, the alternative hypothesis would be that the probability is not 0.6. In other words, we don't know if it's better than what the medicine company claims or whether it's worse than what the medicine company claims. We simply don't know what we're testing here. We're just checking to see if it's right. Maybe it's better, maybe it's worse. Now, the question doesn't look at it from that point of view. The question thinks that the claim is high and expects that there's going to be lower, that there's going to be fewer people who actually experience these reduction in symptoms. So that's why they're doing a one-tailed test. Now, I think from the point of view of an exam question, there'd need to be a little clearer here in the wording of this for you to understand that this is definitely a one-tailed test. Okay, so I think there needs to be another little statement in here saying something like, it is thought that the medicine is not as effective, therefore state the alternative hypothesis. Okay, so anyway, I'm going to go with what the book decides is the correct thing. So the probability is less than 0.6. So there's the null and alternative hypotheses. That's part A done. So for part B, it says, hence find the critical region for a test at the 5% significance level. So if it was not equal to 0.6, we'd need to find a region of 2.5% in both of our tails here. That's a more complicated question, and that's not the question at the moment, so I'm going to go into that. But they're asking here for us to find the critical region. So we want to know at what low level are we pretty sure that we have got a different distribution than the null hypothesis suggests. So, so say for example, we had only 12 people experiencing these reductions. Can we say with a great deal of confidence that we've definitely got a different distribution going on? If we've got 17 people who experience reductions, can we say with confidence that we have a different distribution? Probably with 17 not, probably with 13 yes. But what we need to do is statistically decide that by using a 5% significance level. So we need to trap 5% in here. And if we get a result which is in this 5%, then we can say this is very likely to have come from a different distribution, in which case we would accept the alternative hypothesis. Okay, so that would be saying there's a chance of a 5% or less of us making a mistake and choosing a different distribution over the original distribution. Okay, so that's called a type 1 error. Okay, so 5% in here. So we're going to need to do some cumulative probability with this distribution here. And in fact, for me, I didn't do an inverse binomial distribution, although you can. I just did a bit of trial and error with the binomial CDF. So I put in binomial CDF into my calculator. I put in 30. First number I put in was, I thought, 0 to 14. I thought 14 might be a good choice. And I got the answer here of just over 9%. So I got 9.7% there. So that 14, I would be saying, and remember these are bars in the binomial distribution really, not a smooth curve. So for 14 here, I'd be trapping 9.7%. So that's far too much percentage there that we're trapping. So, so this is not good enough. So we need to look at something which is lower. So then I did 13. So again, I did the binomial CDF, again, 30, 0.6, and then 13. And for that, I'm getting the answer of 4.8%. So at this point, so from 14 and below, so essentially what this is saying is the probability that x is less than or equal to, not 14, sorry, 13, is equal to 4.8%. So this is what we want. Okay, so we can be sure at a 5% level, if we get any number which is lower than 13, that we have a significant result. Okay, so 13 here traps 4.8. It's up to and including 13, 14.8%. So hence find the critical region. This is the critical region. X is less than or equal to 13. When the test is performed, 14 people report a reduction in symptoms. Okay, so 14% of people would be in this region of 9.7% of results in terms of the cumulative probability there. And so that wouldn't be good enough at a 5% significance level. So for 14 people, we would accept the null hypothesis and we would reject the alternative hypothesis here because it's not far enough away from 18. There's essentially a 9.7% chance that we are making a type 1 error. A type 1 error meaning to say that it really comes from the original distribution and that we would be accepting another one with too high a chance of it actually being from the original distribution. Okay, let's just check in the book here their answers as well. Let's see that we've got that one right. So for part 2, again, we've got the critical region right, and it says 13 is less than 14, so not in the critical region, therefore not significant. Therefore, we accept H0, or in other words, we do not reject H0. Okay, guys, thanks for listening. Hopefully that was useful.